So I'll keep recording now. So this is that 24-hour period or so as it started moving on through into through California. And the brighter and the more dense the flashes are, the more lightning was there over time. So it's pretty amazing what we can do with our satellites, right? And what we can image and see. So that was kind of the geo news that you need to geo knows. And if you're just catching the recording now, you can look at the slideshow and you can see what I missed when I forgot to hit record. So there we go. Oh, the last thing I almost forgot. This is also September. It's the Mineral Cup. I don't think I mentioned it to you on Friday, but we're going to be looking at rocks and things moving forward after today. And the minerals are the stuff that make them up. But right now is the Mineral Cup on Twitter. And oops, I think I already have it already opened up right over here. But what's pretty cool about Mineral Cup is every 24 hours, they come up with a new, where'd it go? Hey, Mineral Cup, where'd you go? There it is. They come up with a new voting battle. So tonight's match, or this evening's match, is two iconic minerals, one calcite versus fluorite. Which one will win? And if you want to see all the nerdy geologists go crazy, or even regular people that aren't geologists go crazy about different minerals and stuff, this is it, the Mineral Cup, and they'll tag like which mineral they want to vote for and why it's so good. And it's kind of a knockout to crown the supreme champion of them all, which I think is pretty funny and pretty awesome. So here's some, this is some fluorite. Also, here's some fluorite that when you put it underneath UV light, it glows purple. So you can learn lots of really cool things about these different minerals, different minerals over time. And it's a knockout bracket, like I said. Oop, let me see here where to go. And where we're at right now is right here. So calcite versus fluorite. Serpentine, the California state rock, just survived. It made its way through the round. So you can learn all about these all the way through September. It's pretty fun. It's pretty awesome. It's called @MineralCup. It's on Twitter. Highly recommend it. You'll learn a lot, and you'll see some pretty pictures and interesting, crazy facts of how these things are very impactful to different people and to different things. So, all right, transitioning now into content for the week. So everything, it was all relative. Now it's about those absolute ages. So how are we going to put some of those absolute ages on stuff? So where we're headed tonight, just to kind of give you an idea, is we're going to be talking about radioactivity and what it is. We're going to talk about how do we use, or what tools do we use to measure radioactivity? So there's a couple of different types. There's one that we can like measure it and say there's a lot, but there's one that we can use to precisely basically categorize the exact amount of atoms that it counts, which is pretty amazing and pretty awesome. We'll talk about the different types of things that can actually be dated. So which types of rocks or which types of fossils and things like that can be dated. We're going to talk about, and I need to change this. It should be parent and child material now, where science is finally catching up and changing the nomenclature. So anytime you see daughter here, I need to change that. So it says parent/child ratio. And then, so that's kind of the first part down here is sketch between parent and child. And then how do parent and child ratios let us measure the ages of rock? That's what we're going to be experimenting with tonight. We're going to be looking at it. We're going to be doing one activity that helps you guys explore with that and ask questions. And then we'll use those questions to drive our thoughts as we move forward into the next part. All right. And then let's see here, what else? So here's a half-life description, and then here's half-life depiction number 1. So what I'd like you to do is basically show the half-life graph like you observed in the activity, which you'll be seeing pretty soon. And then another way of depicting it over here is kind of like with dots, and you'll see an example of how to do that moving forward as well. And then you can just kind of fill in the blanks with this sentence down at the bottom. That's just an easy sentence starter. And then for the last thing tonight, for this is the extension question, which is Turlock sits on a lot of sand, and those sand grains, they're broken up pieces of minerals that came from a rock, which came from the Sierra Nevadas, that washed it down into the Central Valley during the last ice age, when we had big floods and rivers coming out of the mountains that were much larger than they are today, because it was a wetter climate and there were just lots of glacial outflow and stuff like that. So anyways, the Sierra Nevadas are 90 million years old, but these pieces of sand arrived in the valley about 20,000 years ago or so, somewhere in that neighborhood. So my question is why wouldn't radiometrically dating the age of the sand grains tell us when the floods occurred and when it deposited the sand? So can you think of a way we might be able to measure the age of sand deposition that occurred 20,000 years ago based on the dating activity game that we're going to be doing at the end? All right, so you're going to see sand grains. Why, if we measure the sand grain and figure out the age of a sand grain, why might not that be useful compared to like when the sand actually got here and became part of the valley? And so we're going to see if we can figure out a way of how we can figure that out a little bit later on. And then for when you watch the Making of North America video, just make a little page with like 4 squares, just come up with a list of 5 places they visited, add a little sketches if you want, some scientific instruments they use to gather data and samples in that movie, some of the scientists' names that they were featured and what their specialties were, and what are some of the 5 stories that are told by the rocks in this video. So if you want to add some sketches, that's totally fine, but writing and stuff here is fine too. It's not supposed to take you forever to do this. It's just to kind of keep you a little honest and help you remember what you watched and what you saw. And that's how that goes. So you can add this to the sketch notes as well. All righty, so that's where we're headed. Now I guess we got to learn about it, right? So how can we possibly know the exact ages of rocks and some of these fossils that are around? Like, for example, this picture from the textbook we used to use before we went free. This is from a picture in Greenland. I've never been to Greenland. I wish I could go to Greenland. But those rocks are 3.8 billion years old. Somebody's gone there and drilled out a small sample, what we call a core, which basically kind of, oops, I don't know if you can see my pen, but it kind of looks like about the size of a Crayola pen. And they pull it out and then they take it into a lab and they can crush up the minerals in there or that make up the rock, crack them open, and basically count some stuff on the inside to help us understand how old they are, which is pretty amazing. So these are 3.8 billion years old. And remember, some of the oldest rocks on Earth, the oldest grains of minerals that we can find, go back about 4.2 or 4.3 billion years. And every year somebody finds a new one in Australia that they date like 4.4 billion or something. But there's a reason why they're not older than that, even though the Earth is 4.5 or 4.6 billion years old. And part of that has to do with the rock cycle on Earth, how it melts things and resets atomic clocks. And remember, when we measure meteorites from outer space, those meteorites, they all have the exact same age and they're leftovers from when the solar system formed. So that's how we get a better age of how old the Earth is and how old the solar system is based on meteorites. So I got to give you a few little pieces of background information here. And that is, the first useful piece is that all rocks on Earth and in the universe, if it's a rock, it started out at one point as a hot molten liquid comprised of various elements. All right, that's what rocks are. And as those rocks cool down over time to their freezing point, basically it allows bonding attractions to arrange atoms into crystal structures. And if those crystal structures repeat themselves over and over and over again, we call those a mineral lattice. And if we had a lab and we're doing lab stuff in here, we take a look at all these in a bunch of different labs, but I'm just giving you the overview right now. So liquid rock cools down, it freezes, turns into solid rock, just like water turns into ice, that's freezing as well. Ice has these repeating crystal patterns, so do the minerals and rocks, okay? But so it makes those. And what's kind of unusual here, though, is that some of the atoms in those crystals, a very, 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 very tiny small percentage of those atoms within the magma that from which these crystals start forming, they have some unstable isotopes in them. They have either too many protons in their or too many neutrons in their nucleus, or something else happens where it changes a neutron into a proton, and they change. And we can count those very precisely these days. And you're going to see those funny small percentages of really, really small kind of imperfections that are radioactive. They help us understand how long ago these rocks have crystallized and formed. So the picture you see on the right, that's Half Dome. Hopefully you've had a chance to see Half Dome in your life. If you haven't, once COVID ends at the end of the semester, I'll put in a sign up sheet that y'all can sign up for. So if we can do a springtime field trip, we take big buses to Yosemite and stuff. If you still are interested, we can all go together as a really big class and go check out Yosemite together. It's a fun day, I promise. So these are what happens when rocks crystallize underground. They make stuff like granite. And then when rocks crystallize above ground, or the lava crystallizes above ground to make rocks, it makes really small crystals that make lava flows and things like that, or sometimes volcanic eruptions. And that's when we got to go to Alaska a couple of years ago. So what does that look like? Not my picture. I've never been this close to lava. The closest I've ever been is about a mile, but still got to see some pretty cool pictures. So how do these mineral crystals form and track radioactive isotopes? Well, they crystallize from magma, like I was saying. So check this out. This is supposed to be melted magma mush up here on the top. And notice as the temperature goes down, as it starts cooling off, it allows more and more atoms to start coming together and make crystals over time. All right. And later on this year, we're going to start talking about as these crystals form, sometimes they become more dense and they start sinking down to the bottom, like you'll see here towards the end. No, it goes down to the bottom, and you can get some other cool rock features from things like that. But the important thing to take away is as this hot molten lava that you're seeing there on the right-hand side, as it starts cooling off and gets below a certain temperature, when it gets to that freezing point and below, the crystals start forming solid mineral lattices out of what used to be liquid rock. So this liquid rock is now turning into solid by crystallizing. And that's the big thing, because crystals, they are going to basically make like jail cells that the atoms, once the crystals are, or the atoms are in the crystals, they can't move, they can't get out. They're basically trapped there unless something heats them up super hot and melts them again. All right, so once they kind of, once they're cooled down and make these crystals, there's no going back. So if you can imagine, this over here on the right is kind of a generic crystal structure of a certain type of mineral that makes up some of the rocks. It's very generic, it's cubish, so you guys can just kind of get an idea of what's going on here. But in order to figure out the exact age of these rocks in Greenland, what we do is we dig into those rocks that are crystallized, that are solid lava now, and we take those crystals, and then we see the crystals that are in here, and we crack these crystals open at the atomic level, and then we literally take the atoms that are in there and we start putting them through special machines that will sort them out. And then once we sort them out, we can do some ratios which are going to help us understand how old they are. So literally the way we measure these, the first step is we have to take the samples, we crush them, and we're opening up this mineral lattice here. And hopefully in these igneous and metamorphic rocks that we'll be talking about later on, there are a few unstable isotopes in there that will change over time. And that's what we're going to be looking at to use to investigate this. So imagine these crystals are down there at the microscopic level. We crack these open, and if you can imagine some of these unstable isotopes kind of like crystal jail, we as scientists break them out of that crystal jail to measure them. And that's what we're going to be looking at in a few moments. So I'm going to play this here for you really fast. I just want you to sit and watch. This is a radioactive element here. I think this is thorium, if I'm remembering right. But I want you to see what's happening. It's in a cloud chamber, which means it's in a really cold little box, clear box with really cold air. And instead of complete air in it, there's a lot of vapor, alcohol vapor. So basically it's evaporated alcohol. It's a gaseous form of alcohol. And when things go through that alcohol really fast, it creates a contrail, just like a jet creates a contrail. So just watch and notice what you hear and then what you see here, and then we'll talk about it in just a moment. watch 51 minutes of it if you really wanted to. So what are some of the things? What do y'all notice and what do y'all wonder about what you're seeing there? So this is a radioactive element that's doing that. So what are you noticing and wondering? Don't all jump in at once. I mean, we don't want to talk across over everybody. So I'll play it again here. Turn it down a little bit with them. So what types of things? Let's go with the easy ones. What are some things you're noticing here? You can chat it, you can say it, however you need. Yeah, what's coming out of it? That's a great question. And then I didn't hear somebody else mention, yeah, the lines kind of evaporate or they go away over time. That's good. Yeah, so I'm not looking for like right answers. I'm just looking for things that you're seeing here. Yeah, it looks like fireworks for sure. Let me ask you this. Does it look like this? Is it hot or cold? That's a great question. So if you're looking at this, what do you notice about the direction of most of these contrails coming off?
It's going outwards.
Yeah, it's like a flower, right? Kind of going outwards, which leads us to believe that it's all coming off of this piece of stuff right here for the most part. And that's true. So this is what radioactivity, quote unquote, looks like if you could see it. But if it wasn't in this cloud chamber, you totally 100% would never be able to see it. And these are little broken pieces of subatomic particles. So pieces of the atom's nuclei that are shooting out and causing a disturbance in the gas that leaves this trail. And you'll notice, do all the let me ask you this, do all the trails look the same?
No.
Yeah, so how would you describe, like, what's different about them maybe?
Some are longer, some are shorter, and then there's like thicker ones.
Yeah, there's thicker ones. And then anybody else see any other differences at all? Yeah, I see some shooting way out. Some look straight to me, like that one was really straight.
Some of them look like faster too, that they come out faster than other ones.
All right,
so to me.
Yeah. And then I also see some, Valeria, go ahead, sorry.
I see some that take longer, like it's as if a string, or some of them that are broken and some of them that are not broken.
Okay. Yeah, interesting. Is anybody else? I see a few that look, some of them look like corkscrews or kind of like screwy, I guess is the best way to say it, like kind of goes or like that. That's what I notice as well. And then I don't know if y'all saw it earlier, but every once in a while you see some funky ones like way off here in the distance that don't look like they're coming from this. And there's a reason for that. We'll talk about that later on. But what we're looking at here, this is radioactive decay. This element is radioactive and it's decaying and spitting off parts of subatomic particles that are inside of it. And the thing that I want you all to know is that it's kind of a random process. We can never predict exactly when one's going to shoot out. We can see sometimes it goes in a flurry, sometimes it's not as much. But if you were to average this over time with another piece of the same element, it would probably be almost the exact same amount of rate over time. So just something to kind of put in your brain moving forward. Here's another quick question. Would you want to hold this in your hand or eat it or anything like that? Heck no. Yeah, so radioactive stuff like this, it can rip through, because they're subatomic, they, depending on the type of radiation, can go right through your cells. Sometimes they'll rip through your DNA, and this is what can cause like cancer and stuff like that over time, or radiation poisoning. So yeah, you definitely don't want to hold things like this. And we'll get into that. And just
where would we find that at?
So this, like pure thorium and things like that, you would have to buy specially, but like if you're familiar with Fiesta ware, it's kind of like a Southwestern glaze, ceramic glaze that used to be popular back in the day. Some of the colors that it was made with were radioactive. So you can take small pieces of Fiesta ware and put them in a cloud chamber and see it fling off like this. If y'all are old enough to remember, before we had LED lights for camping, we had those old camping stoves that had like little bags that hung underneath like a propane gas lantern. And those little bags had some, I think thorium or something in them that was radioactive, and it would shoot stuff off. So there's different amounts of radioactivity. And that's why you can't really buy Fiesta ware anymore, because you don't want really radioactive stuff in your house. But yeah, you might be able to find some dealers on like eBay or something like that for low level radioactive glass. There's people that sell like glass marbles that some parts of the glass used to be in like radioactive nuclear reactors and stuff like that. So they have low levels of radiation, and it's legal for them to sell. So none of these things are going to make like nuclear bombs, but they're not going to be safe to handle. But here's the cool thing, I guess not cool thing. Every mineral on Earth, or every rock on Earth, I should say, if it's an igneous rock or metamorphic rock, it's going to have a slight twinge of elements in it that are radioactive. It's just so small compared to the rest of the rock that it's not dangerous to hold a rock or to lick a rock or anything like that, unless that stuff is really concentrated in it. Luckily for us, there's no rock, not very many rocks around here that are very concentrated in these things. So what is radioactivity? Let me show you what that is. So radioactivity then is just kind of this spontaneous and random breaking of an unstable nucleus in an atom. And that's the one thing I want to make sure we know here, that this radioactive decay, or spitting out of pieces and chunks of those nuclear bits on the inside, it's totally random. We can't predict when it's going to happen, but if we have enough of those over time, there's definitely a consistent rate at which they decay if you add up all the different decays and get an average of them over time. So even though each individual one is random, on a larger scale, there starts to become patterns that are recognizable. And that's what we're going to use to our advantage in just a few moments here. But one of the big types of radioactive decay that y'all might know, maybe, I don't know, from chemistry or physics or something like that, is what we call alpha emissions. And really what happens, if this whole thing in the orange is the atom, so this orange circular thing is the atom, the inside is the proton and the neutrons. In alpha emissions, really what happens is the alpha, the original, what we call the unstable parent nucleus, or the isotope up here, it has too many protons or too many neutrons for it to want to be stuck together. Like, it's just out of balance. So it'll shoot two protons and two neutrons off into the ether. And when it does that, because it's changing the number of protons it has, that changes the name of the element. That's how the periodic table was aligned. You count how many protons an atom has, or an element has, and that's what tells you what element it is. So like hydrogen has 1 proton, helium has 2 protons. So when you go from a bunch of protons and neutrons and you lose 2 of them, and it's going to change the name of the element. And what it changes into is more stable. It's now balanced and it's kind of happy in that state. So it's really happy, and it doesn't turn into anything else anymore. So we call this a child nucleus. Textbooks and stuff still say daughter in it, but last year they started changing it, which is, I think, a really good thing. And this is what we call radioactive decay. So it shoots 2 protons and neutrons off of it, and it changes. And if we had a lot more time and we had labs and stuff like that, we would get into the specifics of this. But for what we're going to be doing in this class, we just kind of need to know the background information here. So there is alpha emission, like I said, takes off the alpha particles, which are 2 protons and 2 neutrons. Then there's also some other weird things that can happen called beta emission, where the nucleus emits an electron. So basically a beta particle is what you can call it, coming from there, and it converts a neutron into a proton. So one of the neutrons shoots out an electron, and hey, it turns in from a neutron to a proton, which basically makes it have 1 more proton in the nucleus and changes its name of the element. It's kind of a weird thing that happens. Or sometimes a stray electron can come through, and that will hit a proton and turn it into a neutron. And so it goes from a neutron down 1 to a proton, and changes its atomic number as well. So what's kind of interesting about that, all of these end results are stable. They don't change afterwards. And what I want you to think about here is these types of atoms, these unstable ones, every once in a while get stuck in these crystal structures I was telling you about earlier. And because they're stuck and frozen in there, once they decay and they turn into a different element, they stay that different element. And the ones that haven't decayed yet, they are also within that crystal lattice as well. And we are going to be able to measure the ratio of how many are changed versus how many aren't changed. And what's kind of interesting is the crystal, or I guess the radiometric time clock on this starts the second those crystals form and they become hard. So that's like when the timer starts, is once it becomes a crystal. So we're going to see how does that help us out a little bit later on. So basically, by the way, coming back to this, those straight particles that were shooting way out that y'all were seeing, those are what we call the alpha particles. So those are the 2 protons and neutrons. Those are like the jumbo jets going flying out far. And then the beta particles are kind of the shorter, curlier Q ones that are going around like that. Right. So that's how those are different. And then the stray ones that you guys saw kind of coming off the edge that didn't look like they were coming from this one. Those are going to be cosmic background radiation. That's kind of leftovers just from other things in the universe emitting them. But the good thing is they're all over the place. They never stop, but there's just so few of them that it's not harmful to us on Earth. And part of our atmosphere absorbs a lot of them anyways too. All right. So here is that periodic table again, just to see how things can change. We're going to be looking at like carbon and nitrogen. So carbon 14 right over here. Maybe you've heard of carbon 14 dating. These date like bones and things that were formerly living. So we can date that with carbon 14, and that undergoes beta decay, which means really what happens is it goes from carbon to nitrogen because one of the neutrons turns into a proton and makes it have 7 protons in its nucleus, which is the number 7 on the periodic table right here. So when we talk about radioactive decay of carbon 14, this is kind of the reaction that's happening, and that's why it's able to change from carbon to nitrogen. And the 14 comes from the total number of protons and neutrons when you add them all up. That's what the 14 number stands for. I'm not testing you on that or anything, but I'm just showing you. Now, that's one way. Another really useful radiometric tool for a scientist in dating rocks is uranium. So there's a really kind of a stable version of uranium, which is uranium-238. And then there's an even more unstable version, which is called uranium-235. But you don't need to know all these steps and all these half-lives. All you just need to know is that uranium-238, it'll turn into lead-206 given enough time. And it takes about 4.5 billion years for that to happen. All right, for one half-life of this to happen, which means if I had a pound of uranium, it would take 4.5 billion years for that pound to turn into a half a pound of uranium. And then the other half a pound would then turn into lead. So half of it would be uranium and half of it would be lead over that amount of time. That's a long time. And that's what allows us to go back and date some rocks. So how do we date these things, right? How do we date these things? Well, there's a couple of ways. Here's that first tool I was telling you about. Geiger counters can measure the amount of radiation. They can kind of quantify if it's a really radioactive or not really radioactive. So if you were to put like a specimen in that cloud chamber, if it was really radioactive, you're going to see stuff flying off of it like we just did. If it was just only a little bit radioactive, you're only going to see, slow things popping off every once in a while. So these Geiger counters, they're the things you see in the horror movies where they go into a radioactive area and it kind of makes those clicking sounds like. And if it's like a really hot area, it goes really crazy. I can't even make that sound or anything like that. But that's what you take out into the field if you want to know if you're being exposed to lots of radiation or not. Like if you're in Utah and some of these places where they mine uranium ores, this is what you want to check. And like this type of rock is called yellow cake because it looks like yellow cake. It's a sedimentary rock, but it has lots of uranium in it. And this is what we use to purify to eventually make atomic bombs and nuclear weapons and things like that. And now to power some nuclear power plants. The issue with that back in the day is when the government really wanted this, they didn't disclose that the radiation was harmful to folks. So there were many, and especially indigenous and Native Americans like Navajo and Diné people down in the Southwest, that government said, we'll pay you lots of money for the rights to this if you mine it all. And they would mine it, and then they would get sick of radiation poisoning very quickly. And it was kind of it wiped out huge amounts of communities when they got sick and died from these things. It wasn't until later that the government kind of finally came clean with what was happening here. But now you can visit some of these areas that are still low enough in the radiation scale that you can stand there for a few minutes and it's not going to do much to you. But you take the Geiger counters just in case. Now, the second way that we can measure these and measure the amount of parent atoms and the amount of child isotopes is using what we call mass spectroscopy. And it's really amazing. And so this is our friend Noah. He works at the University of Kansas, University of Kansas in Lawrence. And what's really amazing is this is a jet-powered vacuum that literally turns crushed minerals into ions and makes it into like plasma. So basically what you see in lightning bolts, it can take those crushed minerals, turn them and heat them up so much they turn into like this ionized plasma, and then it shoots them through these steel tubes. And these steel tubes are powered by a jet engine. I'm not kidding you. It's a jet engine. It's about this, I don't know, the size of I don't know, Hydro Flask or so, a little bit bigger than that. And that jet engine creates a vacuum and sucks that plasma through these areas. And I don't know if you can see on the computer screen over on the picture right here, but literally that plasma kind of gets sent through and then bent with magnets. And when it gets bent with magnets, heavier isotopes are more attracted to the magnets than the lighter isotopes. And so it separates them out. Different types of elements and isotopes get separated out and like spit into different buckets. And from there, they can measure the ratios of, they can use that ratio to determine the age. And then somebody asked, I just saw this question, sorry, says, how is this radiation different than the one they use to treat cancer? It's not. The only thing that is different is the way they use it in cancer treatments. And I'm not a super medical expert or anything, but they take the radioactive elements and they target it and put it in certain areas so that I think it kills like the areas that are cancerous and hopefully like will rebuild better cells that are not as cancerous. But this is where they get some of those radioactive elements from is I'll have to look up where exactly they get the radiation for those from. But yeah, in a lot of those areas, it is definitely radiation has to come from some type of radioactive mineral or something like that to begin with. But that's a good question. I can look that up a little bit further. I would say X-rays though, X-rays are a type of radiation that we can create using electricity. But it's not radioactive decay radiation that we see like from these rocks. So yeah, it's not. And I'll tell you this right now too. Another one is radon, and radon is a radioactive gas that can pile up into your basements, like in the Midwest and stuff. Soils naturally have radon that kind of leaks out and piles down in the butt basement. Radon is not healthy. It's radioactive and is very harmful. And there's some folks now that have been going to mines or something like that, I think in Colorado, and basically sitting in these mines that have high radon counts and sitting in there and breathing it in, trying to treat themselves. And really, they're just going to make themselves very sick with radiation poisoning. So just something to think about in terms of radiation now that I'm thinking about it. This is, that's my wife in the middle there. And that's our other teacher friend, Carolina, who works down in Palm Springs. But yeah, he's telling us how it works and how they plasmatize it and shoot it through. And here's kind of a cartoon version of how those mass spectrometers work. So they take a sample, so it can be either from like carbon or from, if they smash up like different minerals that have uranium or other types of stuff in it, they'll smash it up and they'll heat it up, turn it into a plasma, send it through past those magnets. And then we have this thing called a stripper which kind of strips away some of the extra plasma and stuff that they don't want, and basically allows them to only focus on the elements they want, like carbon or uranium or something like that. And they go through here, and then it goes through another magnet, and then spits them out into different buckets. And we're going to be able to use these different buckets to start measuring half-lives, which I'll show you about in like 2 minutes, 3 minutes or so. So what kind of things can we measure radiometrically? Well, here's the 3 big things that we can measure. All right. The first one is igneous rocks. So igneous rocks are the things I talked to you about at the beginning, where it can cool and crystallize magma or lava. And what does that radiometric date tell us? It tells us how long ago the rocks cooled after they were erupted or after that cooled down in a magma chamber. So granite, this is magma that cooled off under the surface and crystallized under the surface. And that ticking time clock of the radioactive decay starts once it kind of becomes fully solid and crystallized, and none of those isotopes can move around anymore. If it's lava, it'll tell us when it erupted out of a volcano, because that's when it cooled off and turned into, I don't know, I'm not voguing, I'm not doing Madonna, I'm sorry. I'm trying to show like crystal structures being built. I'm just talking with my hands. I just saw myself in the camera. I'm like, oh my gosh, I'm like voguing or something. But yeah, so igneous rocks can be dated. Metamorphic rocks can also be dated. And so metamorphic rocks are ones that have been squished and pressurized under extreme heat. But here's the kind of caveat, is that pressure is not hot enough to melt it. So it doesn't melt it, it just kind of rearranges and breaks some of those crystal structures a little bit and kind of resets things, but it doesn't melt it. And so what does that radiometric date tell us? It tells us how long ago the rock stopped being squeezed and heated. All right. So it tells you kind of a date of like maybe when mountains formed and things like that. And then the third thing that we can date are living organisms, or formerly living organisms would be the best way of saying it. So carbon-14 really gets taken up in plants and photosynthesis and things like that. And because we all eat things that at one time ate a plant, even if we're vegetarians or not vegetarians, you know, plants are the producers of everything on Earth here. There's nitrogen-14 that's in there, and it gets into our bones and our tissues and stays in there until we die. We're constantly replacing it as we eat and as we live. And then when we die, we no longer replace it. And so the carbon-14 that's left in there starts decaying and breaking down over time. And so what we can measure with carbon-14 dates is when something died. But the problem is, I think the half-life of carbon-14 is like 5,730 years, I think, which means it goes away, geologically speaking, pretty quickly. So we can only date things up to about 40,000 years old. Otherwise, all the carbon-14 is like completely changed into nitrogen-14, and we can no longer date it anymore. All right. So here's kind of the big thing in red: melting or high heat and pressure. Those reset the atomic clocks. So when we talk about why Earth doesn't have any rocks that are older than 4.4 billion years old, it's because of plate tectonics on Earth. And it's really hard for a lot of those rocks to kind of just float on the top unchanged for 4.5 billion years. For the most part, many of those rocks have been changed and squished and subducted and remelted and turned into new rocks. It's the rock cycle, basically. So every time it remelts, it resets the clock. And that's how we can tell when the ages of all these different things happened. All righty. So, yep, I'm going to give you like 2 more minutes of stuff, and then we're going to take a quick break, and then we'll come back and we'll work on our first group set of things, and then we'll talk a lot, and then we'll, or you guys will talk a lot, and then we'll go back into our last little bit for the end. So for absolute dating here, these mineral crystals, they act like a sealed container that trap in that parent nuclei. And this is what I was trying to explain earlier. So over time, that radiation can escape, but the daughter or the child material stays trapped inside of that mineral container. So for example, let's say in this, doggone it, let's say in this picture right here, this is kind of the normal mineral crystal, and it has like 4 or 5 isotopes in here that are heavy. Once those crystals are formed, this is when the clock stops, or clock starts. So if I were to take a very extremely fresh piece of cooled off lava, if there were any radioactive things in it, it wouldn't have had enough time for any of those to randomly just decay and be spit out. But the more time passes, they will spit out more radioactive decay. And I guess I forgot to put the orange one there. But what happens is over time, the more time that passes, what you're going to see is more of the child isotopes compared to the parent isotopes, because there's been a lot more time for those to decay and start turning into something else. So that's what scientists look for. We crack open these containers and we measure this parent and daughter ratio. Now you'll see how that works in a little bit with our absolute dating. So how can we use isotopic dating to figure out how long ago a mineral crystal formed? That's what we're about to do. We're going to get ratioed. So let's do a quick favor. It's 5:26. So let's take a 4 or 5 minute, let's take a 5-minute break, and then we'll come back, go get a snack, something like that. I'll explain what we're doing in our groups, and then you'll get to work with your groups for about 15-20 minutes with this part. And then we'll come back and talk a little bit more, and then you'll have another half hour or so with another group activity. Okay. So let's see here. Let's say 5:32. We'll come back at 5:32. So go take a break, go get a drink, go stretch, do what you need to do. 5:32. I'll be right back. Alrighty. Y'all are ready to gather around. I'm stretching my back here. Sorry. When you're all ready, we'll get going. We'll get into our groups and have some fun. I know a lot of folks are still having internet issues and things like that. Excuse me. Alrighty. So here's what we're going to be doing. We're going to be using this radioactive kind of simulator here. This is a screenshot of it, but we are going to be using this to do some notices and wonders in your breakout rooms, not grape-out rooms, in your breakout rooms, in your groups, to try to figure out what types of things do you notice and what types of things do you wonder. So for example, I'm going to click on this. And don't let me forget to send this link out to y'all before we go and do our breakout rooms, but I'm not going to give it to you just quite yet. And that's a very white screen. As I can see, my face is lit up quite well now. But it's going to take it takes 25, 30 seconds for it to load or something like that. They converted this from an old Java to HTML5, so we can all use it on any device, which is pretty cool. All right, and so then this loads. And you'll notice up at the top, we have a couple of different things. There's a half-life tab, there's a decay rates tab, there's a measurements tab, and there's a dating game tab. The one that we're going to be looking at, you guys specifically, is going to be the decay rates. But for this one, I'm going to show you some of this half-life to give you an idea of what we're looking at to begin with. All right, and then let you start organizing and looking at stuff in the decay rates bit. So let's say here's a bucket of atoms. I'm going to put in like, I don't know, how many atoms did I start with here? Let me reset all nuclei. So I'm going to reset it, and then I'm going to press play. So there's 50 in here, and just watch what happens. So this is a chunk of 50 carbon-14 atoms in a big chunk like this, and just watch what happens over time. So I'm just going to let it play here and let it go. So you can see the chunk, and then here it is all represented down here by the actual carbon and nitrogen like that. Whoop. Kind of went off the scale, but after X amount of years, it all turns into nitrogen over time, right? So I can reset it and do it again. It doesn't matter. I can add a whole bucket of atoms and press play and reset things. So, I'm not going to give away the whole game right here or anything yet, or it's not a game, but like what you're observing. But just notice is as time goes on, the carbons turned into nitrogen until eventually there's just no more carbons left. So what y'all are going to be looking at, and the same thing happens with uranium, but notice the time scale has changed a little bit with the uranium over here. So if we press play, it undergoes its decay and turns from uranium-238 eventually down into lead. Interesting things happening here. So it doesn't matter which one of these it goes, it just keeps going. And you could do a custom one. We're not going to do that or anything like that, but that's just kind of the first piece of flavor. I'm not going to explain what it all means just yet, because that's what you guys are going to be looking at and trying to make a little sense of first. So when I send you out to your breakout rooms here, you're going to have Jamboards. And let me give you this to everyone. So here's the Jamboard right here. And basically this will pop you on to, we don't need 19 groups, but I made one with 19 groups in it. Some of my other classes are huge. But here's what you're going to do. You are going to switch over to the tab. I got to find the right one, to where it says decay rates. All right. And with your group, you're going to do the following. If I can find the right, here we go. You're going to do the following. You are going to run the decay rate simulation at least 5 times for carbon-14. All right. So what do you notice and what do you wonder? That's all we're doing is what do you notice? What do you wonder? You can start making some explanations if you think you can describe what's going on. That's totally awesome. You can do 5 different ones. It doesn't have to be with the same amount of atoms, but this is how you adjust the amount of atoms in your bucket of atoms. So remember, go to decay rates right here, and then you can shift this. And then every time you shift it, it restarts. So just let it play and let it run out and see what happens. So what does the stuff on the graph mean? What are all of the axes? What do those represent, right? Those are things to notice and wonder and think about as a crew and as a group. Okay, so run this 5 times at least with carbon, and then do the same thing with uranium. Run it with uranium at least 5 times. So you can do the same one, like you can reset it the same amount and run it 5 times. You can play with it and put a whole bunch and compare a whole bunch versus not very many. Some folks in my other classes, what they've been doing is they've been using, if you're on Windows, they have Snip and Sketch or other screenshot type things. They've been screenshotting stuff. And what that does is it makes a little copy, and you can copy this. And then if you want to go into your sketch, your Jamboard, you can press just Control V like this, and it will paste in your stuff. And then from there, if y'all want, you can like write and say stuff with pens, or you can add sticky notes and do anything that you want there. All right. But that's what you're doing, is add your notices and wonders on this board. Use sticky notes or shapes or drawings to convey your ideas of what you're seeing or what you think is maybe going on. I'm not looking for like right answers or anything. I'm looking for having conversations in your group. What does this mean? What's happening? What do you notice? And maybe you see some patterns emerge. And then the other thing is, just on the orange ones, just please note which are the parent atom and which is the child atom, or the parent isotope and the child isotope. All right, that's what we're going to be doing down there. So let me give you this link. I think I have it so everybody can share. Let me double check. Everybody can share, all participants. Okay. So this might be a thing where you might want to have one person in your group share the screen, and somebody else is like writing down some of the ideas or taking, sketch notes. It's up to you guys how you want to do it, but that seems to work. I am going to give you, this one's not a huge amount of time for this one. I'm going to give you about 8 or 9 minutes, probably 9 minutes or so, to do this and get down as many things that you can notice and wonder. There is no wonder too small. There is no wonder too big, or notice too small or notice too big. Just get out as many things and ideas as you can onto that Jamboard. All right, that's what we're shooting for here. And so here is the what do you call it, simulation. My brain is going a little mushy here after a whole day of doing stuff. So there's this, that link will take you to this, and it'll take, like you saw on my computer, about 20 or 30 seconds to load. It's not indicative of your computer speed. It's indicative of just downloading stuff and things like that. So with that being said, I'm going to put y'all into breakout rooms now, groups of 3, maybe a group of 4, because of just, we have some people down tonight. Oh, wait, no, got exactly 6 groups of 3. Sweet. All right. And introduce yourselves if you haven't worked with each other. If you have, say hi. And then what do you notice? What do you wonder on your Jamboard? Just make sure you go to the correct group page on your Jamboard, and we'll go from there. All right. So don't stress out. No right or wrong. Just what are you noticing? What are you wondering? Oops, I got to put on the right time. Sorry. 9 minutes. All righty. There we go. Hi, Jennifer. Jennifer, are you there?
Yes, I'm here.
Oh, sorry. Hi. Were you in a group or did you breakout room or did you
Oh,
just?
I had to disconnect for a little bit, but
That's totally fine. Can I put you in a room? Is that all right?
yeah, of course, of
All
course.
right. Let's see. They all have 3, so I'm just gonna I'm gonna choose number 3 because what the heck.
Okay.
All right. See you later.
All right, thank you.
All right, welcome back, everybody. So look like you all were chugging along pretty good there. So how about this? Would anybody care to share some aha moments or share some ideas, some things that you saw going on, stuff that you put on the Jamboard, like just kind of stuck out, or other conversations you had?
There was one uranium isotope that literally would just not decay at all.
Ah, so a stubborn isotope, like it just time kept rolling on and just nothing would go, huh?
Endlessly.
Endlessly. Yeah, well, 4.5 billion year half-life could be waiting a while, huh? All right, awesome. What are some other things y'all noticed? They're like, so let me see here.
The
Oh, go ahead.
the difference in the years between carbon and uranium, it looked like so uranium was billions, but I wasn't sure because it didn't say, but it looks like thousands of
Yeah.
years.
It's just
So the
it's just
difference-
years. Yeah, you got it. So 5,000, 10,000. Yeah, so definitely good observations. Carbon has it's not around for as long. Okay. Well, how about in terms of patterns? Like, what did you guys notice in terms of patterns and stuff? Or did you notice any patterns?
We kind of noticed that like there was always one color that had like way more than the other one.
Ah, so at all times, or like at the beginning and the end, or like throughout the
There was one, I forgot which one it was. I might have been the uranium one where when they met, like where they crossed over at the same like billion and the same year time, they
Uh-huh.
had like about the same. It might have been right here. Yeah, it looked like pretty even. And then as the time went on, it one color kind of like went on more.
Ah, okay. Interesting. Good observations. Anybody else have some other ones they'd like to share?
Kind of going off with what she just said, I noticed that at the beginning, it's like changing super fast, but when it hits towards the end, it like slows down like drastically.
Right. Okay. Awesome. That's going to be a useful observation. These are all useful observations, but that one too is going to be very useful. Good stuff. All right. So yeah, we had billions of years down on the bottom. We had half-lives up at the top. And then it says percent of element remaining to begin with. So here's the first thing I want to make mention. All right. We've been running this model with these like isotopes that are in there. Let me get my drawing tool thing. I'm sorry, I guess I already had it open. So I'm going to draw a funny little square right here. And actually I want to make it so it's thicker, and I want to make it, let's make it green just because. I guess that's as thick as it goes. So here's what I'd like you to imagine. I want you to imagine everything in this box is like one part of a mineral crystal, all right, or part of a rock. So some of the minerals in the rock and that isotopes that make that up, it's all trapped. Oops, now I got to go to my mouse. It's all trapped with, doggone it. Sorry. It's all trapped inside of this mineral crystal. And what happens is, depending on the amount of isotopes that are formed in those mineral crystals to begin with, that's going to determine how many parent and daughters you have, or parent and childs that you have as time goes on. But what's kind of interesting is that no matter how many of these isotopes you have stuck within this box, you notice these curves on the bottom pretty much stay the same no matter what. And if you run it over and over and over again, sometimes they kind of cross right over here. Sometimes they cross a little bit beforehand. But if you keep running it over and over and over again, you're going to see that on average, they all kind of cross at where this number 1 is for what we call a half-life. And so there's a reason we call it half-life. And let me just double check that we all understand what's happening with these graphs. These graphs are basically plotting out the numbers of uranium-238 in terms of percentages. All right. So when we started out, we had 100% uranium. And then as time goes on, there's a few little bits of radioactive decay that happen, and they spontaneously change into the lead down here. But what's kind of interesting is right around this half-life, right around this 1 time of half, notice where they cross is generally where it says 50% right here. That is what we call the half-life. All right, so the half-life is how much time it takes for half of the original radioactive material in there, those radioactive isotopes, how much time it takes for half of them to decay, like get rid of some alpha or beta radiation emissions there and turn into the stable child isotope. And here's what happens again. So I'm going to keep playing this. But if you notice, after about 2 half-lives, look, we're about 75% and about 25%. Oh, let me get my pointer, sorry. That would help. We're about 75% now is the lead or the stable stuff, and 25% is the uranium. And so what's kind of cool is after 1 half-life, we had 50% remaining. And if we go half of a half, so half of 50% would be 25%. So after 2 half-lives, it's down to 25%. And then if we go down to 3 half-lives, half of 25% would be, what is half of 25? Like 12.5%, somewhere in that neighborhood. So there's only 12.5% remaining of the original uranium, and about, well, what would that be? 86, 88%, 87.5% then would be the lead up here. So that's what this graph is showing us, these half-lives. The half-lives is how long it takes for half of that stuff to turn into its child amount. And so what's kind of cool is we're going to use these ratios, and scientists have gone to labs and they've been able to measure these basically decay rates. They can't measure 4 billion years because nobody lives that long, but they have super sensitive instruments that measure the average decay rates and how long it would take for them to go away and for half of them to disappear. So that's what they've done in this lab. And so what's kind of cool is if we crack open this mineral that's right here, and all of a sudden we see that, and we crush it open and we stop it right here. So this is where we pull the rock out of the ground. We crush the minerals and we put it through this mass spectrometer, and it comes back with a ratio of about, what is this? About 26%, 26% or 27% uranium, and a whole bunch more, like 75% of lead. What that tells us is, oh, it's undergone almost 2 half-lives, and we can fit it on this curve to figure out exactly how much time has passed. So literally what we're doing when we crack open these minerals is we are trying to find the ratio of parent to child material in there. If we find a mineral where, oops, let me see here. If we find a mineral that is, stop, let me pause it and reset it. If we find a mineral that's all parents, that's going to be brand new. And as time goes on, those radioactive spontaneous decays start happening. And if it's just a kind of a fairly young one, you're not going to see very many child materials, but you're still going to see a lot of parents. So it's just this ratio, and it happens at a known given time frame. And this known given time frame is what allows us to figure out how old actual rocks are and minerals are based on the ratios of parents to the child. It's pretty cool. It's pretty amazing thing to think about. It's like amazing chemistry. And that's why geology and the geosciences, I mean, it's a combination of all the sciences. It's not just looking at rocks or anything like that. That's part of it, but we have to use all these other physics and chemistry and things like that to help us tease out those stories. Biology even, we're looking at like fossils and life and things like that. So just to give you an idea, here are some different currently accepted values of half-lives that we know about. And so this half-life, just in case you want to put it in context of terms for you to describe, it's the amount of time needed for 1/2 of that unstable parent to turn into the child. And the one thing I want you to make sure you know is, like, the whole entire atom doesn't disappear. It just changes from one to the other by a little bit of radioactive decay. So uranium-238 has a half-life of about 4.5 billion years. Uranium-235, much more radioactive and much more active half-life. So it goes away about 713 million years, half of it every 713 million years. Thorium, look at that, 14 billion years. That's older than the universe. Rubidium is very stable, but it still goes away. And potassium and argon also is about 1.3 billion years. So usually when we go drill rocks, these are those isotopes that we're looking for to crush up in a lab and get an age date and try to figure out how old they are. So when I tell you that like Half Dome is 90 million years old, or the rocks that make up Half Dome are 90 million years old, we're using like rubidium and strontium to calculate that. And that's how we can start telling the story of when things happen and putting it in chronological order. All right. So remember, what types of things can be radiometrically dated then? It's those igneous rocks that cooled and crystallized lava and magma. And we generally use like uranium-238 or lead-206 or rubidium and strontium. And these half-lives are hundreds of millions of years. And that's good because we need that to date rocks that are older than about 1 million years. If they're younger than 1 million years, it's hard to date with these ones because the what do you call it, percent error is a little off. So, you know, there's always plus or minus 1 million or 2 years when we get those dates. Uranium or metamorphic rocks, also the same type of thing. We can date really old metamorphic rocks with those. But if we're looking at the carbon-14, that, doggone it, I lost my pointer again. This carbon-14 over here has a half-life of 5,700 years, or 5,730 years, I should say. And so it's really only good for dating things going back about 45,000 years, because after 45,000 years, if we're looking at that simulator, it's all nitrogen-14. There's no carbon left, so you can't take a ratio because it's all nitrogen. And if there's no ratio, we can't date it. All right, so that's the things we can date. So now here's the next thing we're going to do. We're going to go back into that simulator with your crew, and you're going to go. So I'm going to show you an example here on the website. Remember, you just did the decay rates one. You're going to skip this measurement thing, and you're going to go over to the right-hand tab, which is the dating game. Now, you're going to have a funny little, it's supposed to be like a Geiger counter or something like that. But remember, in real life, Geiger counters would not be able to tell you how old something is. But we're going to pretend that it does in this game. And you'll see that there, if I move this over different stuff, we're going to get percentages up here. And in this case, the probe is measuring carbon-14. So what types of things is carbon-14 good at measuring again? What types of things? Really old, fairly young. What types of things were they?
Rocks?
Not quite rocks, not carbon-14. So if we go back, let me go back, carbon-14, it's the living organisms, right? These are the things. So what is radiometric dating for carbon-14? It's like formally living organisms. So things that are made of organic material, wood, bones, skulls, grasses. Dinosaurs would be a good answer, except dinosaurs lived 65 million years ago, so they are outside of the bounds of the 45,000 years of this, of what carbon-14 can do. So that's part of the clue, is then how do we know how old dinosaurs are if we can't directly date their bones? Luckily for us, we can date the rocks, and if the rocks include those bones, maybe we can figure out how old they are. All right, so what y'all are going to be doing is you're going to have to, as a group, you're going to be kind of given a Jamboard, and you're going to try to figure out some of these ages. Now, I want to say right up front, the only two things I want you to really play around with are the carbon-14 and the uranium-238 ones right here. Okay, those are your two choices. Ignore the custom, ignore the error. We don't care about that. It's going to send people on a wild goose chase. All right. Your Jamboards, now this is a Jamboard right here. This is what the Jamboards for your groups will look like. And notice I have little question marks next to each one of these things. Those are what I'd like you to try to figure out the age of. All right. So some of these you'll be able to put right on a rock and figure out the exact age. And some of them, like fossils, you may not be able to put an exact age on, but you'll be able to measure the age of the rocks. So if the rock and the fossil are in the same layer, it's probably right about the same age. Okay, so that's something to think about. So I'm going back to the live version right here. So I'm on carbon 14 right now. And if I go over to there, it says, oh, there's a wooden cup. So this is wood. That's why I'm going to use carbon 14. Ignore where it says check estimates. This is a really finicky thing. And if you're going to spend all day on there, if you try this, all right, so don't even worry about it. Oops, let me see here. So what's kind of cool then is we're at the percent of carbon 14. So what we're going to do is we see if we put it up to this wood cup says, oh, that's 88.2% of its carbon 14, or 88.2% of its carbon 14. The other 12% would be nitrogen 14. So this is the percent of carbon 14 left. And then you're going to move up to the slider here. And here's that rate, that curve, that decay curve that you guys just did and made earlier. And so we know how long it takes for these things to decay. All you have to do is take this and slide it to where the percentage matches the percentage over there. So in this case, if it's 88.2%, you kind of slide it over as close as you can, and you get a ballpark estimate here. So this one only goes to like 88.7. So that's about 1,000 years old. So if I try to go to like 88.2, I can't go there, and this one's 1,046. So it's between that first one and second one. So you just come up with a quick little estimate, and on your Jamboard, you come over here and you'd write like 1,000 years old or something like that, 1,020 years old. Then I'm just going to put YR for years. So that's what I'm going to put right there, and that's how we date the cup. So you're going to do the same thing. If it's organic, bones, stuff like that, keep it on carbon 14. If it's not organic, you're going to try to date it. Like the rocks come up with different ages here. But notice these fossils and these deep layers, let's say if they were dinosaur bones or something like that, notice we can't measure these. So, but there is a rock. So if you find this rock, the age of that rock, by sliding this around to match the percentage up there, then these fossils are probably going to be very similar in age to that rock. Now down here, you might get 3 different ages for each one of these rocks down here. And that's because this was probably like a floodplain or something like that for a long time, where it brought in rocks of different ages to an area. So let's say if you have a rock that's 1 billion years old, a rock that's like 500 million years old, and a rock that's 300 million years old. Those aren't the exact ages, but let's say they were. The age of this layer down here can only be as old as the youngest rock in it. If it's got a 300 million year old rock in it, it has to be at least 300 million years old, but it can't really be much older than that. I mean, we have all these other rocks, or actually, I guess it could be a little bit older than that, but because it has this really young rock in it, we know that it's at least 300 million years old. So you want to take the youngest age. If you're trying to figure out like an average age of this whole entire layer here, go with the youngest age that you find, because that's included in that layer there. So you're just going to measure those. That's what you need to do is you'll try to make sure you're clicking on the right thing, measure the right age. And then once you get the ages of those rocks, can you come up with an approximate age layer over here? And so what you might want to do for those is like add, and I should have probably put in a new sticky note. You could do something like this. Layer A equals or whatever, and then you just bring it down over here to layer A and tell me how old it is. And you can shrink it up so it looks like this. But remember, layer A is going to be the oldest because it's on the bottom, and layer E should be the youngest on the top. And now we're going to see if the radiometric dates play that out. All right, so measure the dates of the rocks, see if we can figure out the ages of them. If you have fossils, these fossils are probably going to be similar in age to the rock in the middle because there's no other way to tell. And then some of these might not work for one, like carbon 14, but maybe it works with a different one. So like, for example, uranium 238 is not getting a reading, but maybe you switch it to carbon 14 and see if you get a rating there. Oh, hey, look at that. I got a reading on that one. So remember, don't try typing it in or getting any bogus estimates right in here. Just get it close and then slide your percentage bar on this time slider here on this graph to figure out how old it is. And that's what we're going to be doing. Then we'll come back, we'll talk about it towards the end, and then we'll send you on your merry way once we figure out how old these rocks are. So this is how we start specifically age dating all of these layers. We know the order. Now we're going to give them some dates. All right. So I think this is like probably 25, 30 minutes, somewhere in that neighborhood. See how, we'll start with 25 and see how y'all are going. And then we'll move on from there. All righty. So let me see. Sorry, I gotta get the breakout rooms open. Like scatter myself once I get talking here. Okay, options. Let's do like 25 minutes and see how y'all go. And if you need me, holler. I'm right here. I'll be watching on the jam boards and stuff. But if you need
Was
me,
there a link for the second jam board?
oh, yeah. Man, you guys are too smart for me. Wanting the actual links to do work. My goodness. Yeah, I moved my chat over there. Thank you. I think this one will work. Let me double check. Yep. All right, I think that's the one. Yeah, it is. I apologize.
Thank you.
ADHD brain, I apologize. So here comes your breakout rooms, and here we go. Oops, nope, sorry, hold on. Okay, open rooms, there we go. All right, now I can talk. Welcome back, unmuted and stuff. So really good job, man. I mean, I know it was only 25 minutes or so, but y'all were able to go through, and I think for anything glaring ideas that I saw needed addressed, I kind of left some notes and things. But y'all did a really good job going through and labeling those and getting them in kind of the ballpark range, I guess would be the best thing to state. So good job with that. One thing I did notice with a few groups to begin with was, especially when we're like at uranium, the BY versus MY. I guess I never really described that, but the MY stands for millions of years. and the BY stands for billions of years. So those units kind of make a big deal. Like if you say 137 BY, that's a lot more than a million years and stuff like that. So that's just one other thing I wanted to clarify before we go forward. Now, let's say if we're out like hunting for fossils and stuff, how do we know how old certain layers of things are? Somebody mentioned earlier dinosaur bones. How do we know how old those dinosaur bones are? Well, basically what paleontologists and geologists go out and do is if they find some dinosaur skulls in sedimentary rock, that's usually what we find them in, is sedimentary rocks like mudstone or sandstone or something like that. You can't really date the sediments. The sediments themselves are just going, if you date the sedimentary rock, it's going to tell you how old the crystals of the sand are. And remember, those crystals came from a bigger rock or a mountain that eventually eroded down and made the sediments to make the sand that buried the dinosaur. So if you measure sand grains and you crush those open, you're going to get a date. It's just going to tell you when that mineral grain was created in the igneous rock that eventually had one time made a mountain that then eroded away. It doesn't tell you when it was turned into a rock. So what do scientists do? They go out and they look for, if there's sedimentary rock layer right here, they look for thin layers of like volcanic ash or lava on top of that layer. And then they try to find some volcanic ash and lava and stuff on bottom parts of layers. And if they can do that, then they can say, oh, the top of this layer is, 100 million years old and the bottom of the layer is 110 million years old. That means it's like somewhere within 10 million years in between those two layers. And luckily in the American West, we have lots of volcanoes through our history and lots of volcanic ash. So there's lots of different volcanic layers that we can get through and date. And after we put things in relative order, we can try to find those bits of volcanic ash that have been erupted out and cooled and crystallized when it erupted and when it put those layers down. And that's how they can come up with kind of these bounding dates, or the high end and the low end based on where it is in the stratigraphic column. So if you try to date, that's kind of the other thing, if you try to date those minerals that are just sedimentary grains, like sandstone, mud, stuff like that, it's only going to give you how old the original host rock was, or the parent rock that it came from. It's not going to tell you how old that sand is. So I bet most of the sand that we find in our yard in Turlock, most of those grains of sand are probably 90 million years old or more. All right. They've just been broken and moved and shifted around in that time. But if we had for some reason, a volcanic eruption, like the Mount Shasta happened to erupt and lay down a new layer of ash in the lake beds and stuff, that would give future geologists a better timeline of when it was laid down and all around it. So great job. Y'all did awesome with that. And I just want to reiterate, remember, we can date igneous rocks, metamorphic rocks, and living organisms. But if you take those crystals in an igneous rock and you melt it, or any rock to begin with, I should say, and you melt it, it breaks those crystal bonds, it resets everything, and all the radioactive daughter material goes by the wayside. So it resets the timer. All right. So igneous rocks and metamorphic rocks are the things that we can date. And the timer starts the second those crystals cool off and make the crystal structures. So you did that. We're done, probably going to be done just a little bit early here. So just reiterate your, sketch notes. So we talked about what radioactivity is. We talked about the different tools to measure it. How can we date things, right? So sketch each group of things. Those are the three that we just talked about. Quick little sketch showing the parent / child material trapped in a crystal lattice. I showed you a few examples of that. You can do your own artistic impression. And then in here, what's a half-life? You can Google the definition of half-life. It's also in the notes. But this #1 depiction, this is kind of the half-life graph that we were looking at. So over time. And then this half-life depiction right over here is kind of like looking at the dots. So remember, we started out with a full box of one color dots, and then after one half-life, it was 50-50 colored dots, and after another half-life, it was like 75-25, etc. That's what we're looking for there. You can fill in the sentence frame down at the bottom, and then the extension question is, again, with that sand, measuring those sand grains, what's it going to tell us? And can you think of a way we might be able to measure the age of sand deposited? And I kind of mentioned that the same way how we measure dinosaurs and stuff like that. Look for igneous rocks we can date, and usually that comes in the form of volcanic eruptions or something like that. So like a thin layer of volcanic ash, and that's what we'll go for. So next week we're going to take a look at some patterns in plate tectonics and trying to figure out, how did all these rocks get organized the way they did, and then we'll learn about some of these rocks and go on some really cool virtual field trips and have some fun with that. So you guys jammed right through it. We're done a little bit early tonight, so congratulations and good job. And I got nothing else for you except have a good weekend. And wait, look, there's a chat. There's a chat. Hold on. Is there only one correct answer to that extension question? You could come up with different variations, I suppose, but yeah, there's kind of one overriding big answer of why, like if you dated that sand grain, it's only going to tell you one specific thing. And that specific thing I've talked about a little bit. So, yep, that's what we're talking about.
I have a question.
Yeah, go ahead.
So on the modules, I saw the rock cycle. Was that part for the whole semester, or was that for the first week? Like in the notes, the sketch, the rock cycle. Do we do that in the sketch notes?
In our module?
Yeah, it says something about the rock cycle.
Okay, let me see here.
Was that just for the first?
Was it on the notes tonight or on?
No. I think it was for like the first week. I was just.
Oh, okay. Let me see here. Oops, that's Tuesday, Thursday. Hold on. It's late on Friday and I'm drawing a blank here. So let me double check and see. All right,
Are you
let me
talking
go to
about the 3D rock model? We didn't go
Oh,
over
the
that.
three.
Yeah.
Okay, so the
Yeah.
3D rock. I see. Okay, yeah. So this
Yeah.
one was, if you click on that, it was a Jamboard that folks did. We never got around to doing this, and that's right. Somebody asked me about this because their sketch notes were a little bit different. We skipped this one, so you guys don't have to do this one. We didn't get a chance to really get into it or go big on this. So yeah, you can totally skip this one, but what it does is if you did follow the link, it would take you to oops, let me see here. It would take you to a three-dimensional model of the rock that looks like this. And by the way, while you guys are doing this, looking at this, let me give you the link for the sunshines and blues, because I almost forgot to do that again. So here's your sunshines and blues link, and then you guys can do that. But here is, oops, where'd it go? Oh, it opened up in a new tab. That's why. But it would open up this 3D model. And so this is what some of our classes got around to looking at, but we didn't get a chance to look at it in our class. So yeah, you can ignore that little parts for the sketch notes.
Okay, so that had to be. Okay,
Yeah.
thank you.
Okay, I was confused, but now I'm not. It makes total sense. So. And yeah, if you leave a little comment on the Jamboard, you're good to go. And that's it for tonight. And I'll see you all on, I guess, next Friday. Hope you stay healthy. I know it's been really rough for a lot of folks these days. So take care of yourselves the best you can. And if I can do anything to help you out, let me know. Okay. Oh, yeah, go ahead, Valeria.
So